Hello, Math Studies students. In this lesson, in our 6.1 through 6.3 notes, we're going to take a look at some very basic calculus. Calculus is a branch of mathematics that really allows you to study real world situations. Up until this point in your mathematics classes, you have used mathematics to study situations that are very simplistic. However, calculus allows you to go way beyond that. Calculus is sometimes called the study of things that change constantly. So that's more like real life situations. And so those of you that go on and take calculus next year, you will learn mathematics that will allow you to apply math to more real life situations. So today what we're going to look at is one of the basic ideas in calculus, and that's the idea of the derivative. So to get there, let's start with this first example. It says the graph below represents a company's profit over a few months. I'm going to underline this, describe the rate of change at the following times. So let's take a look. This is profit versus time. So it looks like profit increased for a while, then leveled off, and then started to decrease. So let's examine what's happening at 1 month. So at 1 month, that's right here. I think everyone agree that at this point the company's doing pretty well. Profit is increasing, and I think we could even describe it by saying it's increasing rapidly. So we're going to say that at 1 month, profit is increasing, and we're going to say that it is increasing rapidly. Okay, now let's take a look at what's happening at 2 months. So at 2 months, let me put a point there, we can see that the profit of the company is still increasing, but it looks like at this point it's not increasing as rapidly as it was at 1 month. So we're just going to describe that by saying that profit is increasing, but we're going to say increasing less rapidly than it was at 1 month. Okay, and then what about at 5 months? Over here at 5 months. Okay, so the company is still making profit, but remember, we are just thinking about the rate of change at that point. So at this point, the profit is on its way down. So the company's still making money, but the profit is not increasing at this point. The rate of change, it's decreasing, and I think we could say it's decreasing. I'm going to say somewhat rapidly at that point. It looks like as time goes on and profit continues to decrease, it decreases a little bit more rapidly. So here's another interesting question. Was there a time when the rate of change was zero? In other words, if the rate of change is zero, that means that profit was neither increasing nor decreasing. So if you look at this graph, it looks like right about here, somewhere between 3 and 4 months, okay, we can see that at that point, profit was neither increasing nor decreasing. So the company was making a profit at that point, but the rate of change was not changing. It was not the rate of change was not increasing or decreasing. So we're going to say yes, that happened. Yes, and it happened somewhere between 3 and 4 months. Now, those of you that go on to study calculus, you'll be able to find that actual x value where that happened. Okay, so now let's go on and talk about why we can qualify these increases and decreases as rapid or less rapid. Well, we can do that by studying the instantaneous rate of change at a time t. Okay, that instantaneous change at a time t can be represented by the slope of the line that is tangent to the curve at time t. So let's go back and look at what was happening at 1 month. Okay, so at 1 month, let's see what was happening here. So what we could do is we could look at the line that is tangent to the graph at that point. So you remember from your study of geometry that a tangent to a curve would be a line that touches a point at exactly 1. So if you look at this red line, it has a positive slope. Now let's compare that slope to the slope of the tangent line at this point. So I'm going to draw a little tangent line there. So you can see that that tangent line, it also has a positive slope, but it's less steep than this tangent line was. That's why we said that at 2 months, the profit was growing less rapidly than it was here. At 5 months, okay, let's draw that tangent line. So that tangent line, you can see that tangent line, let me draw that one more time because I'm trying to make it appear that it touches the curve exactly once, okay? So we can see that that line has a negative slope, and it's somewhat steep, isn't it? So at that point, the company was still earning a profit, but the rate of change was decreasing somewhat rapidly. And then that last point we talked about, that point between 3 and 4 months, if we draw that tangent line, notice that it's a horizontal line. Well, you'll remember from your study of Algebra 1 that the slope of a horizontal line is 0. So that means that the rate of change was neither increasing nor decreasing at that point. So let's talk about this topic of calculus that allows us to describe the rate of change of a function at any particular point. That topic is called differentiation. Differentiation. Differentiation is an algebraic method of finding the equation of the gradient function. As you recall, gradient is the IB word used for slope. Okay, so the gradient function, the function that generates the gradient or the slope of the line tangent to the curve. So in other words, we can do an algebraic manipulation of a function to find the function that would produce the slope of this line, or the slope of this line, or the slope of this line, or the slope of this line. And that's called differentiation. Okay, so other names for the gradient function, okay? Sometimes it's called the derivative function. That's what you'll mostly hear if you take a calculus class next year. It's called the derivative function. And one name I kind of like for the derivative, and it's not a technical term, but I like calling it a slope generator, because remember, a function produces output values, so the derivative function is a slope generator. In other words, if we put a particular x value into the function, it's going to generate the slope of the line tangent to the point at that tangent to the curve at that point. So now let's talk about some notation. If a function is written y equals, okay, if it's written in that form, then the derivative of the function is represented either by this notation, dy over dx. What that means is the derivative of the function with respect to x, or sometimes you'll see it written y prime, okay? If the function is written in the form in standard function notation, f of x equals, then its derivative will look like this, f prime of x, okay? So dy dx or y prime, let me make that prime a little bit more prominent. Okay, dy dx, y prime, or f prime of x are all ways that we can notate or write the derivative of a function. Okay, so now let's learn the rule for finding the gradient function or finding the derivative of a function. So if we have a function y equals a times x to the n, to find its derivative, I'm going to write it dy dx equals, I could have also written y prime equals, so either of those works. But what we're going to do is we're going to take this exponent of n, and we're going to bring it around front and multiply it by the coefficient. So in other words, it's going to be n times a to the x. So again, you'll start by bringing the exponent of x around to the front of the term, multiplying it by the coefficient, and then the next thing you're going to do is you're going to decrease this exponent by 1. So instead of x to the n, now it's going to be x to the n minus 1. Okay? If it's written if a function is written in function notation, f of x equals a times x to the n, then to find the derivative f prime of x, we will take n times a to the x. Again, that happens by taking that derivative around to the front and multiplying it by the coefficient. And then we're going to decrease the exponent on x by 1, n minus 1. Now, one thing to note, and you'll see some examples of this in a minute, this process is valid for all values of n, okay, so for all exponents, both positive and negative. So now let's look at some examples so you can get the hang of differentiating a function, finding the derivative. So in this example, we're going to differentiate each of the following. In other words, we're going to find that function that produces the slope of a line tangent to the curve at any particular x. So our first example is y equals 4x squared. So now, to write the derivative, I'm going to write dy dx. If I wanted to, I could have written y prime equals. But to find the derivative, I'm going to take this exponent of 2 around to the front and multiply it by 4. 2 times 4 is 8. So this is going to be 8x to the, and then what we're going to do is decrease this exponent by 1. So 2 minus 1 equals 1. So you can either write 8x to the first, or you could just write it 8x. So we could write our answer like that, or if you prefer, if you want to use the notation y prime, we'd say y prime is equal to 8x. Okay, let's take a look at the second one. So if f of x equals 3x to the fifth, if we're going to differentiate or find the function that's the derivative, we're going to take that exponent of 5, bring it around to the front, multiply it by 3. So that means f prime of x is going to be 15x to the, now remember you have to reduce this exponent by 1, so 5 minus 1 would be 4. Okay? So now let's look at this next example. What if the function has more than one term? Well, what you do is you just apply the rule to each term individually. So let's look at number 3. So to find f prime of x, okay, let's first of all find the derivative of just the first term, 3x. Now, you don't see the exponent. There is an exponent, and that exponent is 1. Okay, so if I bring the 1 around and multiply it by 3, well, 1 times 3 is 3. And then it's going to be 3 times x to the 1 minus 1. Okay, so remember there's this invisible exponent of 1. 1 minus 1 is 0. And of course, x to the 0 is equal to 1. So whenever you have a term that is of degree 1, the derivative is just going to be its coefficient. Okay? Let's move on to the next term. Now, when we take a look at this term, remember the sign in front of the term belongs to the term. So this coefficient is actually negative 4. So we're going to take the exponent around to the front and multiply it by that coefficient of negative 4. So 2 times negative 4 is negative 8. And then we need to take that exponent and decrease it by 1. 2 minus 1 is 1. So you can write the 1 if you want to, but it's not required. All right, and then the last term, x to the third, well, the coefficient is invisible, but the coefficient is 1. So we would bring the 3 around and multiply it by 1. 3 times 1 is 3, and it's positive 3, so that would be positive 3x to the, don't forget to decrease this exponent by 1, 3 minus 1 is 2. Okay? How about number 4? Well, this time we have v as a function of t. So to write the derivative, we could either say dv dt, that's the derivative of the function v with respect to t. So what I'm going to do is take this 8 around front, multiply it by 4. 8 times 4 is 32. So that would be 32t to the, decrease that exponent by 1, so it would be t to the 7th. Or another way you could write that would be v prime equals 32t to the 7th. Okay? All right, how about this next function? F of z equals 3z to the 4th over 2. I'm going to write that just slightly different. Let's write it like this. F of z equals 3/2 z to the 4th. So that way it's a little bit clearer that the coefficient of this z term is 3/2. So what we're going to do to find f prime of z, to find the derivative, we're going to take 4 around front and multiply it by 3/2. So I'm just going to do this work over here. 4 times 3/2. 2 goes into 2 once, 2 goes into 4 twice, and 2 times 3 is 6. So 4 times 3 halves is 6. So this is going to be 6z to the, now we're going to decrease that exponent by 1, so it's 6z to the third. Okay? Now this next one, before we differentiate, if we're going to differentiate it term by term, we need to go ahead and multiply these two binomials together. So whatever method you're used to, you could use FOIL or box method, whatever you call it, they're all the same. It's just a matter of taking these two terms and multiplying them by these two terms. So I'm going to rewrite this function, g of t, when I multiply everything out, that would be 3t squared. Let's see, the outside terms would give me 12t, and the product of the inside terms is negative 1t. 12t plus negative 1t is 11t, and that's positive, so that would be plus 11t. And then I'm going to multiply the last terms and get negative 4. Okay, so now we can differentiate. So g prime of t is going to be, I'm going to bring the 2 around front, multiply it by 3, and then decrease 2 by 1. So that would be 6t plus the derivative of 11t is just 11. And then I guess this is the first time this has happened. What would be the derivative of a constant term? Well, if you think of the function y, whoops, let me write this down. If you think of the function y equals a constant, that's going to be a horizontal line, right? Let me jot that down. That's a horizontal line. And as you know, the slope of a horizontal line is always 0. So that means that the derivative of a constant will always be 0. Okay, so if g of t is 3t squared plus 11t minus 4, then the derivative g prime of t is 6t plus 11. Okay, let's take a look at number 7. And again, I'm going to rewrite this function a little bit differently. Remember, when you have a positive exponent in the denominator of a fraction, that's the same thing as a negative exponent in the numerator. So I'm going to rewrite this function y equals 4x to the negative second. Let me just write the property that I just used. 1 over a to the n is equal to a to the negative n. So a positive exponent in the denominator is the same thing as a negative exponent in the numerator. Okay, so now when I go to find the derivative, dy dx, or if you want to, you can write y prime. I'm going to take this negative exponent and multiply it by 4. So negative 2 times 4 would be negative 8 x to the, now remember, you have to decrease the exponent by 1. If I take negative 2 and I subtract 1 more, that's going to take me to negative 3. So be real careful when those exponents are negative. When you go to subtract 1, be careful with your arithmetic. Negative 2 minus 1 more would be negative 3. Another way we could write this, if you prefer, you could write y prime equals negative 8x to the negative third. Okay, so let's do one more. I'm going to rewrite number 8. I'm going to rewrite it as f of x equals 12 fifths, that's our coefficient, times x to the negative third. Now, remember this exponent of 3 only applies to the x. It has nothing to do with this 5, okay? So that means I'm going to take this x to the third and move it up to the numerator and call it x to the negative third. So now when I go to find f prime of x, I'm going to take negative 3 times 12 fifths. I'm going to write that a little bit better. Hold on just a second. Make it a little bit clearer. Okay, negative 3 times 12 fifths. Okay, so what I did is I took this exponent, bring it around front, multiply it by the numerator, and then times x to the, I need to take negative 3 and decrease it by 1. Negative 3 minus 1 more would be negative 4. Okay, and then just simplifying a little bit, f prime of x would be, let's see, that would be negative 36 fifths. I just multiplied the numerators times x to the negative fourth. Okay, so now that you've practiced the mechanics of finding a derivative, let's look at an application. So let's talk about calculating the gradient of a curve at a given point and what that means. So in this example, we have the graph of f of x equals 2x to the third minus x squared minus 4x plus 5 is shown below. So here's the graph of our function. So we're going to differentiate the function. In other words, we're going to find the derivative function, and then we're going to find the gradient or the slope of the function at these indicated x values, okay? Then once we've done that, we're going to comment on the behavior of the function at each of those x values based on its derivative. Okay, so that's a lot of directions. Let's take it one thing at a time. So the first thing we're going to do is we're going to find the derivative of this function. So if f of x equals 2x cubed minus x squared minus 4x plus 5, let's find f prime of x, taking it term by term. So our first term, we'll bring the 3 around front, multiply it by 2, and then decrease this exponent by 1. So our first term is going to be 6x squared. And then the next term would be minus 2x to the first. Remember, we brought the 2 around, multiplied it by this negative 1. So that would be negative 2x, and then 2 minus 1 is 1. Minus, remember, the derivative of a degree term is just its, of a degree 1 term is just its coefficient. So that would be minus 4. And then the derivative of any constant term is always 0, so we're done. So this is our derivative function. F prime of x equals 6x squared minus 2x plus minus 4. Okay, so now the next thing we're asked to do is, let's say, find the gradient or the slope of the function at the indicated x values. So in other words, we're going to find the slope of a tangent line to this curve at the point x equals 1. Well, to find, let's just kind of find out where that is on the graph. So at x equals negative 1, excuse me, I think I said 1 a minute ago. So that's right here, okay? So let me just sketch the tangent to the curve at that point, okay? So what we're going to do is use this function. Remember, we call this a slope generator function. So this function is going to generate the slope of this green tangent line at x equals negative 1. So in other words, we need to evaluate our function f prime of x at negative 1. So that means everywhere I see an x, I'm going to put in a negative 1. So that would be 6 times negative 1 squared minus 2 times negative 1 minus 4. Okay, so let's do that arithmetic. Let's see, we'd have 6 minus 2, nope, plus 2, because we'd have negative 2 times negative 1, and then minus 4, that's 8 minus 4, so that is equal to 4. Okay, so what this means is that at x equals negative 1, the slope of the line tangent to the graph at that point is positive 4. So now I'm going to have you write out a sentence. Those of you that take AP Calculus next year, I'm trying to get you used to the verbiage that you'll need to use when you're in AP Calculus. So what we're going to say is the following. We're going to say that the graph of f of x is, we're increasing. Now, the reason why we say that it's you know what? We're just going to abbreviate because that's what you'll do a lot next year. Those of you that take AP Calculus, we're going to say the graph of f of x is increasing where? At x equals negative 1. And then we want to say why is that? And the reason why is because f prime of negative 1 is positive. Or sometimes you'll say f prime of negative 1 is greater than 0. That's another way of saying that it's positive, okay? So we were asked to comment on the behavior of this graph at x equals negative 1 using the derivative. So we just make the statement. The graph of our function f of x is increasing where? At x equals negative 1 because the derivative at negative 1 is a positive value. So that means the tangent line has a positive slope. Okay, let's try it again. Let's evaluate the gradient function or the derivative function at 0. So in other words, we're going to find f prime of 0. So f prime of 0 would be 6 times 0 squared minus 2 times 0 minus 4. So that simplifies to negative 4. Okay, so what does that mean? That means at 0, let's just indicate that point on our graph. So at x equals 0 right here, okay, the tangent line looks like this, doesn't it? Okay, so let's comment on the behavior of this red function at the point x equals 0. So we would say the graph of our function f of x is decreasing where? At x equals 0 and y, because f prime of 0 is negative. Or you could say f prime of 0 is less than 0, okay? So at this point, x equals 0, we know that the function, the red function, that's the graph of f of x, we know that it is decreasing because at that point we have a negative derivative, okay? How about at x equals 1? Well, at x equals 1, that's this point, okay? So what would that tangent line look like? It would look like this. It's going to be horizontal. So I bet you can guess what the value of the derivative is going to be. Let's go ahead and evaluate that. So at x equals 1, that means we're going to evaluate f of, sorry, let me get the right color here. We're going to evaluate f prime of 1, so that would be 6 times 1 squared minus 2 times 1 minus 4. Again, I'm evaluating the derivative at x equals 1, so that means everywhere I see an x, I'm putting, oh, nuts. Everywhere I see an x, oh, sorry. Everywhere I see an x, I'm putting a 1 in, okay? So let me scroll back down there. So 6 times 1 squared minus 2 times 1 minus 4 gives us 6 minus 2 minus 4. So 6 minus 2 is 4, and 4 minus 4 is 0, and that's what we expected. Remember the graph? Let me go back there. Remember the tangent to the graph at x equals 0 was a horizontal line, okay? So let's comment on the behavior of the function at x equals 0. So we will say that the graph of f of x is neither increasing nor decreasing at x equals 1 because f prime of 1 is equal to 0. All right, so let's do one more. Let's take a look at x equals 2. So I'm going to scroll back up to the graph. So at x equals 2, okay, that's right here. Let me sketch that tangent line. That's a positive slope. And notice that it's a little bit steeper than this was, so we should get a positive number that's bigger than 4, shouldn't we? Because at x equals -1, the slope of the tangent line was 4. So I'm going to redraw my tangent line because it doesn't really look like a tangent. A tangent line should touch a curve exactly one time. Okay, that's slightly better. Okay, let me go back and evaluate f prime of 2. So that means go back to your derivative function at the top of the page. Everywhere you see an x, you're going to put in a 2. So that would be 6 times 2 squared minus 2 times 2 minus 4. So 2 squared is 4, and 6 times 4 is 24. So we would have 24 minus 4, and then minus 4 again. So 24 minus 4 is 20, and 20 minus 4 is 16. So we get a positive number 16, and as expected, we got a bigger positive number than we did when x is equal to, what was that, -1, the first one we did. So our comment would be that the graph of f of x is increasing where? At x equals 2 and y, because f prime of 2 is positive. Or if you prefer, you could say f prime of 2 is greater than 0. Okay, so now you're going to take a look at a worksheet and do some problems like on these notes. So you might want to keep these notes handy, and if you have any questions, be sure and let me know.